Hi, we're going to get started with a new unit today. Hopefully, the readings that you did before were somewhat informative, somewhat thought-provoking, and I'm actually kind of glad if you walk in with more questions than you have answers at this point. If you need time to try and think about these, I want you to hit the pause button. Excellent. Compared to non-metals in period 2, the metals in period 2 have a larger. Which one is bigger? You can kind of look at table S if you need help with this. You can kind of look at your periodic table. Ionization energy goes up as you go from metals to non-metals. So does electronegativity. So does atomic number, because that's how the table's built. So it's atomic radius. Again, going period 3 left to right, they're going to get less metallic. So the metallic character does not increase, and the electronegativity goes up. Carbon to attract electrons. This is electronegativity. It should be less than both. Going this way on the periodic table, the trend should be ionization energy goes down. Remember that these are smaller atoms, these are bigger atoms, and if we're going to pluck out one electron from them, the outermost electrons are held with a weaker force, and therefore less energy is needed to be put in to get the electrons out. Very unfortunate situation took place in November of last year. Acid and bleach mixed together to generate toxic fumes, and I asked you to read this, and there's a bunch of links in there. I don't know how helpful the links were in spurring your thoughts, but some of the bigger questions that I got are these here. Why did it create toxic fumes? Why are they incompatible? Why did the mixture change color? I thought was one of the best questions to ask, because that tells me chemistry is going on. And so it appears to me that there's this branch of chemistry that you all are less familiar with. Now, some people did mention acid and base chemistry, which is a good thought to have, but this isn't exactly just acid-base chemistry. This kind of chemistry works in and out of almost every other unit we've seen. This scale clean and super 8. I'll include some readings so that you can take a look at what is actually contained in there. Some people went on to do some reading. I think chloramine was something that someone mentioned. I can't remember if it's in here or not. Green and bubbling should be pretty clear what was going on. Not only is chemistry everywhere, like you really have to pay attention to what you're doing and what other people around you have done. Just cleaning a room can have some really bad consequences if you're not aware of what's been in the room and what's going to be in the room later. So I wanted to quickly walk through these answers and questions that I gave you and see how the answers changed. What I'm going to do is I'm going to write chemical reactions that correspond to what's going on. And based on this, it would be clear to me that if rust is an example of oxidation occurring, then if rust is when metals are exposed to air and oxygen's in air, then it would make sense that most people would say oxygen is required for oxidation to occur. Looking at the second question, we have a single replacement between aluminum metal and copper 2 chloride, and that should make aluminum chloride. It's a single replacement reaction, and copper. Now looking at this, if this is still oxidation, I'm a little confused why people are still saying oxygen is required for oxidation to occur, because there's no oxygen. The loss of electrons, well, that works. Only metals, yeah, that still works. The only common thread between the two is the fact that metals are present. The last thing I have to mention is this. I highlighted the one answer because you can see the other got a lot larger here, and I did that on purpose. The one thing that people seemed to think that 2/3 of answers seemed to contain was that oxidation is the loss of electrons. I want to step into this Haber process. First off, it is an equilibrium. This nitrogen is covalently bonded. This hydrogen is also covalently bonded, and then in ammonia, they're covalently bonded. So we're going to come back to this, but I'm really confused as to why people are saying that electrons are lost when we went from sharing electrons to sharing electrons. Let's start with that first example. This isn't an example of iron rusting, it's an example of copper rusting. The definition of oxidation was gaining oxygen into the compound or combining with oxygen. The thing I didn't really mention is that oxidation is only one half of a two-sided process. You can't have one thing happen without it happening somewhere else. That is to say, this is a very simplistic reaction, but there's always this other half called reduction. Loss of oxygen, or breaking with oxygen. It's a little bit harder to see in this reaction, but I'm going to give you a second reaction that will show this a lot better. So we saw the reaction for iron rusting. There's actually a chemical way to get iron unrusted. In this reaction, you might be able to see it a little better. If oxidation is the process of combining with oxygen, you can't combine something with oxygen without taking oxygen from somewhere else. It's a little harder to see in the initial reaction because you're only combining it with an oxygen, but I guess one way of thinking of it is that one of the oxygens kind of goes over and joins up with the copper. So it's pretty clear to see if you look at this reaction that this oxygen goes over and joins that oxygen to turn CO into CO2. So in this case, the substance that gets oxidized would be carbon monoxide, and the substance that gets reduced is the iron oxide. And there's always two in one of these standard reactions, these oxidation reduction reactions they're called. And from here on out, I'm going to abbreviate this because chemists don't like writing a lot. They call this a redox reaction. They have to happen together. You can't have one happen without the other. So it was seen that oxygen managed to do certain things, and so when oxygen does what it does, we called it oxidation. That being said, to look at these two reactions, once we got a little bit better with our understanding of chemistry, we saw that there were several things that did what oxygen did, just that they weren't oxygen. Now, to look at this, these two reactions are similar. In the process of making an ionic compound, though, this goes from a neutral atom to a copper ion, and this goes from a neutral atom in a covalent bond to a chloride ion, just as this becomes, from the swap rule, Cu2 plus and O2 minus. So we go from not being charged to being charged. So a different way to look at what oxidation is when you combine with oxygen, what happens to atoms that combine with oxygen. And in this example, we can see when copper combines with oxygen, it loses electrons to oxygen. And so this is consistent with our old definition, because if you gain oxygen, the oxygen takes electrons away from something else. So in any case of losing electrons, you can see that the top reaction actually matches up with the bottom reaction because they're both showing copper losing electrons. The other side of this is reduction. The other half, electrons can't disappear. And in this case, I guess the safest thing to say is that the thing that gains electrons is reduced, while the thing that is reduced in the second reaction is actually oxygen. Oxygen is not really oxidized. Oxygen is reduced, which makes sense if you think about it. If oxidation is something else getting affected by oxygen, I don't think oxygen is going to affect oxygen. And I don't think many things are going to out-oxygen oxygen. Have I said it enough today? I'm not done yet. There are two ways to remember this definition. It is a slightly older definition, but it is the one that makes the most sense, and so it's the one we keep referring back to. Many of our examples will include it. There are two different mnemonic devices. I like oil rig. Oxidation is losing, and reduction is gaining. The problem is you have to remember that the thing that is being lost and the thing that is being gained is electrons, which the other mnemonic is, Leo the lion says Gur, lose electrons, oxidation, gain electrons, reduction. Either one works. I can't write vertically very easily, but these definitions do both stick. However, none of this applies to reaction 3 because there's no oxygen, there's no metals, and you're going from covalent bonds to covalent bonds. But maybe, by looking at a similar reaction to the Haber process, we can maybe see that there is actually oxidation occurring if we look at the electrons and how the electrons change. So here's an example of a very straightforward, simple oxidation reaction, oxidation reduction, redox reaction. Hydrogen and oxygen react to make water. Is it oxidation? Yes, because oxygen is present. So what's nice about those older definitions is what was happening there is still oxidation, and it's not like we're suddenly going to say, oh, that isn't oxidation. But when we get a clearer picture and a better definition, it should still be honest to those original reactions and fully explain it. That is to say, if electrons are lost and oxygen is present, then the thing that is oxidized is the not oxygen. So pretty much I can look at this and I can say that the hydrogen should be oxidized and the oxygen should be reduced. But that's not really what the question is. I'm just going by our first definition, so that should still be true going through. So let's draw out some Lewis structures. Here are our reactants, and here's our product. And I think I'm going to want a different color. So how does the sharing of electrons compare in the reactants and products? So looking at these electrons, how are they shared? Looking at these electrons, how are they shared? Why would we say these are shared equally? Well, if we go back, the En values are equal. Right? When the electronegativity values are equal, the sharing is equal, and so both get an equal share of the shared pair. We've covered all that. Looking at our products, though, these are not equally shared. We've spent a long time talking about oxygen, and remember that in an OH bond, oxygen with the higher electronegativity will have a slight negative. Hydrogen will be a slight positive, but well, that's it, isn't it? The oxygen now in water has more than equal share of electrons, and the hydrogen now in water has less than equal share of electrons. So really, we're going to define oxidation as even a partial loss of electron density. What's neat is that if we look at that as a definition, now we can define many, many, many reactions as oxidation, even though there's covalent bonds and you're not losing and gaining electrons, even though oxygen may not even be present. So looking back at our reaction, which chemical was oxidized, which chemical was reduced, and why does this still make sense? How does this show that our electrons are lost and gained? So I think the answer, I'm going to switch back colors so we can talk about this. But I think the answer is going to be shown right there, there, and there. So nitrogen having a higher electronegativity than hydrogen will show a slight gain of electrons. So the nitrogen will actually end up reduced because of this process, and the hydrogen will end up oxidized. So oxidation and reduction, redox reactions, we're always going to refer to the reactants and saying what got oxidized and what got reduced because of the reaction. But the idea is that in our reactants, the nitrogen and hydrogen both show equally shared electrons, but because it's unequal in the products, the hydrogen undergoes a slight loss of electrons. Is it a full loss? No, because it's still sharing. It's just sharing less equally than before. Just to put more terms onto this, because it's not confusing enough, I just wanted to show and give you another example of something like older school. This really only shows up, I think, on the SAT too. So if you ever see it, I just want to mention it. Oxidizing and reducing agents. Agent here is kind of taking the word Well, you guys know what an agent is. Like, if you have an agent for like an actor or an athlete, the agent is the person that goes out and gets something for the other person. They go do the work, they go talk to people, they go make things happen. So an oxidizing agent is the thing that makes oxidation happen. It helps something else to get oxidized. And the only way to help something get oxidized is to, well, the best way, if a substance was going to help oxidation occur, hey, that thing's trying to lose electrons, I mean, I'll take them. The oxidizing agent will actually gain electrons and oxidize something else by getting reduced. This is really confusing, I know, but if you think about it as the agent makes it happen, it does the opposite. If you have that definition, the reducing agent also will lose electrons by getting oxidized. The reason we had these older definitions was we were trying to define what we were observing in nature, and if you look at it that way, the oxidizing agent is the thing that gets reduced, and in this case that's oxygen. Oh, well, that makes sense. Oxygen is the oxidizing agent because oxygen makes oxidation happen to something else. And then the reducing agent is, in this case, of course, copper. And just to put a little bit of more information into that for you, for anyone who's still looking at the SAT too. So as a summary, just to really line things up, anytime you're looking at a chemical equation, any chemical process, if oxidation and reduction are occurring, these things are true. If these things aren't happening, then you would call it not a redox reaction, but we're not going to get into that too much until the next lesson. In general, losing electrons is oxidation, gaining electrons is reduction, and that losing and gaining may not be a full loss or gain. Even if it's a partial loss or gain, we still call it redox reactions. Thanks for watching.